Welcome back to the deep dive, everyone. Today we are getting into the nuts and bolts of building the Internet of Things, the IoT.
Right, which is just a massive topic.
Oh, totally. We're using the book Designing the Internet of Things by Adrian McEwen and Hakeem Kesmili as our main source today. And the mission of this deep dive is really to demystify how a magical smart object goes from just an abstract idea, right, to a physical prototype, and then scales into a real manufactured product.
Yeah, and we'll also get into the ethical baggage it carries along the way, which is honestly pretty significant.
For sure, because, we hear these buzzwords all the time, but if you actually understand how a smart umbrella or a connected alarm clock is built, it gives you this profound advantage in understanding modern technology.
Exactly. You stop just seeing the glossy exterior and start seeing the systems underneath.
Right. Okay, let's unpack this. So before we even talk about circuit boards and code, we have to understand the actual design philosophy of a successful IoT device.
Yeah, because it is definitely not just about slapping a screen on a refrigerator.
No, that usually just makes it annoying.
It really does. The authors actually draw on this concept from Mark Weiser. He was at Xerox par ARF, and he coined this idea called calm technology.
Calm technology, I like that.
Right. The premise is that technology should exist on the periphery of our attention. It should basically just quietly hang out in our environment and only take center stage when it has something really critical to tell us.
Because our attention is a finite resource.
Exactly. And a brilliant early example they talk about is the live wire, or the dangling string, created by Natalie Jeremijenko back in the 90s.
Oh, I remember reading about this. It's literally just an 8-foot piece of plastic string, right?
Yep, just a string attached to a small electric motor on the ceiling. But the motor was wired directly into the office's local computer network. So every time a packet of data traveled across the network, the motor would twitch.
That is so cool. So it just gives you this ambient information without demanding your focus at all.
Exactly. If the network is fine, the string just hangs silently. But if there's a massive data surge, the string whirls around violently and makes this physical humming sound.
So you don't have to stare at a dashboard. You just kind of process it as ambient weather in the room.
Exactly. You just feel the health of the network.
And building on that, David Rose introduced this concept of enchanted objects, which I find fascinating.
Oh, yeah, it's a great concept.
The idea is that the best IoT devices don't look like tech. They look like artifacts from fairy tales that fulfill these deep human needs, like omniscience or protection or human connection.
Right, like an enchanted sword or a magic mirror. And a modern example they give is John McCarroll's Wear Dial. Have you seen this thing?
I have. It's basically a physical clock that sits on your mantelpiece, but instead of time, it points to where your family members are.
Exactly. It syncs with their smartphones, and the hands point to categories like work or traveling or home.
Which is literally just the Weasley family clock from Harry Potter.
Oh, wow. Yes, that is exactly what it is.
It's the exact same fantasy parallel.
Yeah.
But I have to play devil's advocate here, because the book also mentions the sorcerer's apprentice metaphor.
Right. The broomsticks multiplying out of control.
Yeah, like if we enchant everyday objects, say a Roomba or a smart lock, without fully understanding the underlying magic, aren't we just risking them running out of control and making our lives chaotic?
That is the exact risk, which is why to build these enchanted objects safely, we have to put a really reliable brain inside them.
Right. And how do you even choose the right hardware for that?
Well, what's fascinating here is how much the economics have changed. The cost of computing has just plummeted.
Oh, it's wild. Like an old Intel 486 chip used to cost as much as a small car, right?
Exactly. And now you can buy that equivalent computing power for the price of a chocolate bar.
That's just mind-blowing.
It really is. So you have options. You can use microcontrollers or system on chips, SOSACs. The classic entry point for hardware is the Arduino.
Right, the Arduino.
Yeah, it's a microcontroller. It's great for beginners because it uses a deterministic memory model. There's no bulky operating system getting in the way. It just runs your code in a predictable, infinite loop.
They say blinking an LED is basically the hello world of hardware on an Arduino, right?
Yep, exactly. It's highly predictable.
I like to think of the Arduino as the human nervous system, like a reflex.
Yeah.
It's simple, instant, and reliable. You touch a hot stove, your hand pulls back instantly.
That's just a great way to look at it. But sometimes you need more than just a reflex, right? Sometimes you need to process video or run a database, and that brings us to the Raspberry Pi.
Which is more like the conscious brain.
Exactly. It's a tiny, powerful PC running Linux. It has way more processing power, but the trade-off is it draws significantly more energy, and it actually requires booting up, which introduces latency.
So if you're building a smart umbrella that just blinks when it rains, a Raspberry Pi is total overkill and will drain your battery immediately.
Exactly. You have to match the brain to the task. And then there are devices like the Electric Imp, which try to make the connectivity part incredibly easy.
Right, the Imp. That thing is the size of an SD card, isn't it?
Yeah, it's tiny. And what's wild is how you connect it to Wi-Fi. You literally hold your smartphone screen up to it, and the screen flashes light pulses to transmit the password.
That is so sci-fi.
Yeah.
Just beaming the password via light.
It's super clever. But the downside is it relies on a closed source, cloud-managed system. If the company behind the Imp ever shuts down their servers, your device becomes a plastic brick.
Right, because it entirely depends on their proprietary cloud, which is a huge risk.
Huge risk. And that actually brings us to how these brains talk to the outside world, because a brain trapped in a plastic shell isn't the Internet of Things, right?
Right, it needs to communicate. It needs to give the object a voice.
Exactly. And they do that through APIs, application programming interfaces, but the format of that communication really matters for these small devices.
Because they have limited power and memory.
Right. Historically, web services used XML to structure data, but XML is heavy. It has all these opening and closing tags for every single piece of information.
Oh, I know. It's so verbose.
Oh, yeah. So if a tiny battery-powered device has to parse a massive XML file just to find out the temperature, it wastes a ton of processing power.
So they use JSON instead, right?
Exactly. JSON is the preferred lightweight data format. It just uses simple key-value pairs, which is way easier on constrained devices.
They give that example in the book of the Clockadillo API.
Oh, yeah, the task timer.
Yeah, it's this physical timer that just sends simple JSON updates over HTTP-like duration, complete or cancel. Super lightweight.
It really is. And the book also talks about the danger of scraping data instead of using official APIs.
Oh, like trying to scrape weather data or football fixtures from a public website.
Right, because if the website changes its layout even slightly, your code completely breaks. Plus, there are legal and copyright risks to scraping someone else's data.
Definitely. But even with official APIs, how you ask for the data is important, right? Because HTTP is a request-response cycle.
Exactly. Which causes network strain.
It's like polling.
Yeah.
I always compare HTTP polling to a kid in the backseat of a car constantly asking, are we there yet? Are we there yet?
Yes, and the server just keeps saying, no, no, no.
Right. It wastes so much energy for both the kid and the parent.
Totally. Which is why the industry developed MQTT. It's a lightweight publish-subscribe protocol specifically designed for devices with limited bandwidth.
So how does that work in the car analogy?
In that case, MQTT is like the parent saying, look, go to sleep. I will wake you up when we get there.
Oh, that makes so much sense. The device just sleeps until the server pushes the new data to it. Much more efficient.
Massively more efficient. It saves a ton of battery life.
So, okay, let's say you've figured all this out. You've built a working prototype on a breadboard. Let's say it's a tweeting bubble machine, like the Bubblino example from the book.
That was a fun example.
It really was.
Yeah.
But how do you turn that single fragile prototype into a mass manufactured product and like an actual viable business?
Well, the transition from craft prototyping to mass production is tough. You have to move away from those messy breadboards and start routing electrical tracks on custom printed circuit boards or PCBs.
Right, because those jumper wires will just fall out.
Exactly. So you use software to design the board, and you output what are called Gerber files.
Gerber files?
Yeah. You send those files to an assembly house, and their machines read them to know exactly where to put the copper and drill the holes.
Okay, so that handles the electronics. But what about the physical case?
For the enclosure, you have a few options. You can use 3D printing, which is great for complex shapes, but slow for mass production. Or you can use laser cutting or CNC milling.
Gotcha. So you get it manufactured. But then how do these companies actually make money? Because it's not just a traditional retail model anymore, is it?
No, it's really not just make a thing, sell a thing. If you sell a connected device once, but you have to pay to keep the cloud servers running for 10 years, you'll go broke.
Oh, wow. Yeah, that makes sense. You have ongoing server costs.
Exactly. So companies have to get creative with business models. A lot of them pivot to subscriptions or freemium models, or they become infrastructure providers instead of selling consumer gadgets.
Like that company Amay mentioned in the book.
Yes, AMI. They are an environmental data consultancy. They put sensors everywhere to track the real-time carbon cost of manufacturing, say, a bag of coffee beans.
That's incredible.
Right. And they make their money selling that data and consultancy to corporate clients, not selling the physical sensors to regular people.
Okay, but let me push back on something else regarding manufacturing. There's this huge tension between open source and closed source hardware.
Oh, definitely.
If you make your design open source like Arduino does, what stops a massive factory overseas from just downloading your schematic, mass producing it, and completely undercutting you on price?
Well, honestly, nothing stops them physically. And clone boards are everywhere. But the authors argue that open source isn't about protecting the plastic. It's about building a passionate community.
Okay, so the community is the real product.
In a way, yeah. When you open source your hardware, that community stress tests it, they build new software libraries for it, and they provide free technical support for each other.
So they basically do your R&D and marketing for free.
Exactly. They create this massive mind share that a copycat factory simply cannot replicate just by copying the copper traces on a board.
That makes a lot of sense. The brand loyalty protects you.
It does, but, once you scale up and millions of these devices are actually placed in our homes and our cities, they create a massive, massive web of data.
Which brings us to the ethical ripples of a connected world. Because there is absolutely a dark side to these enchanted objects.
A very dark side. And it usually comes down to who owns the data and who is watching.
Let's talk about the Westfield shopping mall in Australia, because that blew my mind.
Oh, yeah. That is a perfect example of what can go wrong. So they installed camera sensors in their parking garage to help people find their cars via an app.
Sounds super convenient on paper.
Right. But a security professional named Troy Hunt decided to investigate it. He found out the app was requesting data from the server using unencrypted JSON feeds.
Wait, unencrypted, so anyone could just see it.
Anyone. If you were on the network, you could intercept the feed. And it wasn't just your car. You could see the full license plates and parking durations of every single car in the lot.
That is terrifying. It's basically an open surveillance database just handed to anyone with a laptop.
Exactly. And it highlights the shift from aggregate data to individual data, which the book talks about a lot.
What's the difference there?
Well, aggregate data is like a power company using smart meters to balance the electrical load for an entire neighborhood. It's helpful and mostly anonymous.
Right, just look at the big picture.
But individual data is when that smart meter is monitored so closely that someone can tell exactly when you wake up, when you use the microwave, or when your house is empty.
That's crossing a huge line.
It really is. And we also have to think about the environmental ethics. All this IoT stuff requires rare earth metals.
Yeah, the physical cost of the cloud.
Right. It creates massive electronic waste and a huge carbon footprint to keep millions of devices constantly connected to servers.
So what does this all mean? Like, if our objects are constantly collecting data on us and our neighbors, do we even truly own them anymore? Or are we just like beta testers for massive data brokers?
That's the big question. And if we connect this to the bigger picture, it really highlights the necessity of the Open Internet of Things definition.
Which is what exactly?
It's a proposed standard demanding transparency. It argues that users have a fundamental right to know what their devices are doing, what data is collected, and who it's shared with. Without that transparency, you can't maintain public trust.
Absolutely. Because a smart home isn't very smart if it's secretly spying on you.
Exactly.
Well, we've covered a ton of ground today. We started with the whole philosophy of calm technology, keeping things on the periphery.
Right, the live wire and the wear dial.
Yeah. Then we looked at picking the right physical brain-like, choosing a simple Arduino over a power-hungry Raspberry Pi.
And we talked about how they communicate efficiently using JSON and MQTT instead of heavy XML and polling.
And then the messy reality of mass manufacturing custom PCBs, figuring out a business model that won't bankrupt you, and of course, the massive data privacy and ethical minefield we just discussed.
It is quite the journey from an idea to a finished ethical product.
It really is. And before we go, I want to leave you with a final thought that was directly inspired by the text.
Oh, I like this one.
Yeah. The book notes that early digital camera phones actually had fake mechanical shutter noises added to them.
Because people were freaked out by silent photography.
Exactly. Society was terrified of surreptitious invisible photos. So they added that fake click just to let everyone in the room know they were being observed.
It was a social signal.
Right. So as every single chair and umbrella and thermostat becomes a connected sensor, what kind of fake shutter noises will we demand for our everyday objects?
Ah, that's a brilliant question.
How will our environment signal to us that we are being watched when everything is a camera or a microphone? It's something to really chew on.
Definitely.
Well, we highly encourage you to check out Designing the Internet of Things by Adrian McEwen and Hakeem Kasimli. It is an amazing resource if you want to dive deeper into all of this.
It really breaks the hardware and software down beautifully.
Remember to subscribe so you catch all our future deep dives. Have a great day, friends of the show.